Now, now we will study a triangular wave generator. A triangular wave generator can be formed by simply connecting an integrator to a square wave generator. So you know that there are two stages. First one is square wave generator. After that, integrator. We will represent A1 as the first one having an amplifier of A1, and second integrator is having an amplifier A2. Or you can say the square wave generator as A1 and integrator as A2. The input of the so here the triangular wave requires that phi R3C2, we'll see what it is. Phi R3C2 must be greater than T by 2, where T is the period of the square wave. As a general rule, R3C2 should be equal to T. So here, yes, to obtain a stable, what I told that the previous when I explained about an integrator, to obtain a stable triangular wave, what we need to do is we should connect a resistor parallel to C2. We to connect a resistor parallel to C2, that is known as C4, that should be equal to 10 times R3. So now we'll see the circuit. This is the circuit. As I told that we already explained about how the square wave generator is working, how the integrator works. Here the square wave that is given to an integrator, we are getting a triangular wave. For stability purpose, we connect a resistor R, as you can see that it is R4 across C2, and yes, in the previous what we explained is, we explained that 5R3C2 should be, yes, 5R3C2 should be greater than or equal to T by 2. 5R3C2 should be greater than or equal to T by 2, or at least the condition is R3C2 should be equal to R3C2 should be equal to R3C2 should be equal to T. So here you can see how the waveform you are getting. So the output of the first square wave you are getting, when it is positive, the output of the integrator is negative going ramp. When the square wave output is negative, then the integrator output is going from positive to negative to positive. Now already in the previous example you come across that uh, during the positive side, positive, yeah, when the signal is, the square wave is positive, output is the expression itself is minus 1 by R C integration of V, like that. So it is a minus, so which indicates that it is going to negative. Now here, yes, the frequency of the triangular wave generator is limited by the slew rate of op-amp. So there were high slew rate op-amp such as LM301 should be used for the generation of relatively higher frequencies. That is to be considered. Now another triangular wave generator which requires fewer component, that is shown in figure. So here what we are going to see that we are see here, this is also a triangular wave generator. It uses fewer components. First one is a comparator and the second one is an integrator. Okay, so here the waveform is same as previous one. You can see that the waveform is same as previous one. You are getting a triangular wave generator. So the second one is integrator and first one is a comparator. So it is more easy. Now when you are observing it, you can see that when the value of P just greater than 0, when the value of P just greater than 0, it is going positive. When the voltage at P just below 0 voltage, then the output of this goes to negative VSAT. It's a comparator. When P is positive, just slightly positive greater than 0, it will be saturated to plus VSAT. When P is slightly less than 0 voltage, it will go to negative saturation. So you are getting a square wave. Now when the square wave is applied to a integrator, what happened is, you already studied that output is with a minus sign. So during the positive, during plus VSAT, the output is negative going up. Okay, so it will attain a maximum voltage of minus V ramp or plus V ramp, minus V ramp or plus V ramp. Yes, so here the important things you should remember is, one side of, you know that if you are considering this, the R2 is connected to the output, R2 is connected to this, R2 is connected to the output, R3 is connected, and R2 is connected to the integrator output, and R3 is connected to the comparator output. Now when the comparator output is plus Vsat, this will, the output of integrator is negative going, and this R2 and R3 forms a voltage divider. One side it is plus Vsat, other side is minus Vramp. When this integrator output reaches minus Vramp, that time the voltage at P is become slightly less than 0. So output of the comparator become minus Vsat. When this output of the comparator is minus Vsat, that is applied to the integrator. So output of the integrator going from minus Vramp to plus Vramp. When it reaches plus Vramp, the potential at P is slightly greater than 0 voltage, so output become again plus Vsat. This is the working. Once more I will tell that the first comparator works on the potential at P. When P is slightly greater than 0, it becomes plus Vsat. P is slightly less than 0 volt, it becomes minus Vsat. Now, when the so here when the comparator output is plus Vsat, the integrator output is negative going ramp, and when it is just reaches minus Vramp, that time the potential at P become slight negative. That means it is slight less than 0 voltage. That time output is become minus Vsat. Which output? The comparator output become minus Vsat. When the comparator output is become minus Vsat, integrator output is positive going ramp, and it may reach to plus Vramp. When it reaches plus Vramp, the potential at P become slightly above positive, that means above 0, and output the output of comparator become plus Vsat. So the potential at P, it will go to just below 0 voltage and just above 0 voltage, and the voltage at P is varying from slight minus 0 and slight positive 0, that means above. So this is the waveform. Now when you are relating the equations, you know that when the output is minus Vramp, output of the comparator is plus Vsat. Just before it reaches minus Vramp, the potential at P is 0, So what we can do is the R2 is connected to output of the integrator and R3 is connected to VSAT. So we can equate this minus VRAM divided by R2 is equal to minus plus VSAT by R3. So minus VRAM by R2 is equal to minus plus VSAT by R3. So minus VRAM is equal to minus R2 by R3 into plus VSAT. Similarly, when your input signal output become plus VRAM, the potential at P will become slightly above positive. That time plus VRAM by R2 is equal to So could you tell me why we are getting a minus sign here? Why we are getting a minus sign? So when you are again go back to the why you are getting a minus sign? Because when one is positive, other is negative. When one is negative, other is positive. So that is why. And when it is positive, it is a negative. Because of that, when it is negative, it is positive. So that is why we are getting minus VRAM. Similarly, when the output is plus VRAM, we are getting plus VRAM is equal to minus R2 by R3 into minus VSAT. Now output is varying from minus VRAM to plus VRAM. V0 peak to peak is equal to plus VRAM minus VRAM. So you are getting it as V0 peak to peak is equal to 2 times R2 by R3 into VSAT. This is positive, this is negative. So plus VRAM minus of VRAM. So it will become 2 times VRAM. So plus VRAM is equal to 2 times R2 by R3 into VSAT. Now the time can be calculated from the integrator output equation, substituting V1 is equal to minus VSAT, V0 is equal to V0 peak to peak. So V0 peak to peak is equal to minus 1 by R1 into C1, and integration 0 to T input is minus VSAT and the constant is assumed to be 0. So we are getting it as VSAT divided by R1 C1 T by 2. From that you can calculate the T by 2, that is equal to V0 peak to by VSAT R1 into C1. So V0 peak to peak, we know that what it is, that is already given here. Substituting all those things, you will get T is equal to 2R1 C1 V0 peak to peak by Vsat. Substituting this, you are getting T is equal to 4R1 C1 R2 by R3. F0 is 1 by T, so it is equal to R3 divided by 4R1 C R2. So please go through this. The revision is not very tough. Simultaneously, you can open your text also. Text is not much clear, okay, but still you can study.